What if the sky above you is not silent, but slowly rotating? Right now, you are traveling around the center of the Milky Way galaxy at nearly 220 kilometers per second, completing one full orbit every 225 to 250 million years. Above you stretches a barred spiral galaxy about 100,000 light-years wide, containing roughly 100 to 400 billion stars. Tonight, on Velorin's Sleepy Space Mysteries, we gently drift through our galactic home, from its glowing central bulge to its quiet outer halo, exploring how gravity holds hundreds of billions of suns in a slow cosmic dance. These are not myths, but measured distances in light years and velocities in kilometers per second. If calm journeys through space help you relax, subscribe, like, turn on the notification bell, and consider joining our membership to support deeper explorations. Before we continue, comment where you're listening from. Let's see how far this signal travels across Earth. Now, let's begin. If we could rise gently above our galactic home and look down from far beyond its halo, we would see not chaos, but structure. A vast rotating disk of light, thin and luminous, stretching roughly 100,000 light-years from edge to edge. Within that disk, hundreds of billions of stars move together in a slow and patient orbit around the center. This is the living body of the Milky Way, a rotating ocean of starlight in which we are quietly embedded. The galactic disk is not a single uniform layer. It has depth and texture. Astronomers describe two main components: the thin disk and the thick disk. The thin disk is where most of the Milky Way's visible stars reside. It is relatively narrow in vertical height, only about 1,000 light-years thick in many regions, but it spreads widely across the galaxy's diameter. This thin disk contains the spiral arms, the gas clouds, the bright blue stars, and the stellar nurseries that continue to shape the galaxy even today. Above and below this thin disk lies the thick disk. It extends several thousand light-years in vertical height and contains older stars, ones that move in slightly tilted orbits compared to the flat plane of the thin disk. These stars are generally more ancient and contain fewer heavy elements. They are relics of earlier epochs in the galaxy's formation, when mergers and gravitational disturbances stirred the Milky Way into a more turbulent shape. Over billions of years, the thin disk settled into a calmer, more orderly rotation, while the thick disk preserved the memory of earlier cosmic events. Within the thin disk are the spiral arms. These arms are not solid structures like the blades of a fan. They are patterns, density waves that move through the disk like gentle ripples in water. As gas and stars orbit the galactic center, they drift into and out of these arms. When gas clouds enter a spiral arm, they are compressed. That compression triggers star formation. New, massive stars ignite, shining brilliantly in blue and white. For a few million years, they illuminate the arm, outlining its curve before drifting onward. Our own sun resides in a smaller spiral feature known as the Orion Arm, sometimes called the Orion Spur. It is a modest bridge of stars situated between the larger Sagittarius Arm and the Perseus Arm. From our position, about 27,000 light-years from the galactic center, We orbit quietly within this structure. We are not near the crowded, energetic core. We are not in the sparse outermost edge. We inhabit a middle region, stable enough for billions of years of planetary evolution. At this distance from the center, our solar system travels at roughly 220 kilometers per second. That means every second, we move about 220 kilometers along our galactic path. In an hour, that becomes nearly 800,000 kilometers. And yet, because the Milky Way is so vast, it takes approximately 230 million Earth years to complete one full orbit. This period is called a galactic year. To say it gently, since the Sun formed about 4.6 billion years ago, it has completed only around 20 galactic orbits. Dinosaurs rose and vanished within a fraction of a single galactic year. Entire mountain ranges formed and eroded in less than one turn around the center. The disk rotates steadily, but its timescale dwarfs all human history. The rotation of the disk is not like the rigid spinning of a solid wheel. It is differential rotation. That means different parts of the disk move at different speeds. Stars closer to the center orbit more quickly in terms of angular speed, completing their circuits in shorter times. Stars farther out move with different orbital periods. However, unlike a simple solar system where outer planets move much more slowly, the Milky Way's rotation curve remains surprisingly flat. Even stars far from the center orbit at speeds not dramatically lower than those nearer in. This behavior hints at something profound. The visible stars and gas we can see do not account for all the mass required to keep the outer regions moving so quickly without flying apart. When astronomers estimate the Milky Way's total mass, including its vast dark matter halo, they arrive at a figure between 1 trillion and 1.5 trillion times the mass of our Sun. Most of that mass is not in stars. It is invisible, exerting gravity silently, holding the disk together like an unseen scaffold. Within the disk, interstellar gas weaves between the stars. This gas is mostly hydrogen, accompanied by helium and traces of heavier elements. It exists in multiple phases. Some of it is cold and dense, forming giant molecular clouds that can span hundreds of light years. Other regions are warmer and more diffuse, forming a thin mist between stellar systems. In the coldest and densest clouds, gravity begins its quiet work. Small fluctuations in density grow over time. A region becomes slightly denser than its surroundings. Gravity pulls in more material. The cloud fragments. Eventually, cores form that collapse under their own weight. As they compress, temperature rises. When the central temperature becomes high enough, nuclear fusion begins, and a new star is born. These star-forming regions are often visible as nebulae, glowing in soft pinks and reds when illuminated by ultraviolet light from young stars. They are scattered along the spiral arms like lanterns floating in a current. Over millions of years, the newly formed stars drift away from their birthplaces, and the clouds disperse or are reshaped by stellar winds and supernova explosions. The disk, then, is not static. It is a cycle. Gas forms stars. Stars live and shine. Massive stars explode, returning heavy elements to the interstellar medium. That enriched material becomes the next generation of stars and planets. The thin disk is both a nursery and a graveyard, a place of continuous transformation. All of this unfolds within a structure rotating like a vast, luminous sea. If you imagine the Milky Way not as a rigid object but as a slow ocean of light, each star is a droplet following the pull of gravity. Waves of density ripple outward. Currents of gas flow between regions. Spiral arms brighten and fade as stars are born and die. And through it all, our sun continues its journey. 27,000 light-years from the center. 220 kilometers per second through the dark. One galactic year every 230 million Earth years. We are passengers in a rotating disk that is both immense and delicate, bound together by gravity and shaped by time. If you are still listening as we drift through this rotating ocean of stars, gently type 1 in the comments. The structure of the galactic disk becomes even more remarkable when we slow down and examine how motion and mass work together to maintain this vast rotating system. At first glance, you might imagine that stars orbit the center of the Milky Way in the same way planets orbit the Sun, with gravity pulling inward and motion carrying them forward. That comparison is helpful, but only up to a point. The galaxy is not dominated by a single central mass alone. Instead, gravity arises from the combined pull of hundreds of billions of stars, immense clouds of gas, and an even larger halo of unseen dark matter. Every star contributes to the gravitational field. Every cloud adds weight to the rotating disk. Together, they form a self-gravitating system in delicate balance. When astronomers measure the rotational velocity of stars in the disk, they find something fascinating. Near our position in the Orion Arm, about 27,000 light-years from the galactic center, the orbital speed is roughly 220 kilometers per second. To picture this calmly, imagine traveling around Earth's equator at about 1,670 kilometers per hour. Now multiply that by more than 100. That is the quiet speed at which the sun moves through the galaxy. Yet we feel nothing unusual because everything around us shares this motion. The Earth, the Moon, the other planets, and even the surrounding stars are all participating in the same grand orbit. Motion on this scale becomes invisible from within. What makes this rotation especially interesting is that it does not slow dramatically with distance from the center. In a simple gravitational system, such as planets orbiting a star, the farther objects are from the center, the slower they move. This is because the gravitational pull weakens with distance, and less speed is needed to maintain orbit. But when astronomers map the Milky Way's rotation curve, plotting orbital speed against distance from the center, they find that beyond the inner bulge the curve remains nearly flat. Stars tens of thousands of light-years outward still orbit at speeds close to 200 kilometers per second. This observation tells us that visible matter alone cannot explain the galaxy's structure. If only the stars and gas we can see were present, the outer disk would not be gravitationally bound strongly enough to sustain such high speeds. The stars would drift away over time. The fact that they do not implies the presence of additional mass, distributed broadly throughout and beyond the disk. This mass is attributed to dark matter, an invisible component that does not emit or reflect light but exerts gravity. When we include dark matter in our estimates, the total mass of the Milky Way rises to roughly 1 to 1.5 trillion times the mass of the Sun. That immense mass forms a gravitational well deep enough to hold the rotating disk together. The disk itself is not perfectly flat. It gently warps at its outer edges, bending slightly upward on one side and downward on the other. This warp may be influenced by interactions with nearby satellite galaxies or by uneven distributions of dark matter. Even so, the overall structure remains coherent, rotating steadily over billions of years. Within the disk, stars follow nearly circular paths, but not perfectly so. Their orbits can shift gradually over time due to gravitational interactions with spiral density waves or nearby stars. This slow migration means that a star is not forever fixed at one radius. Over hundreds of millions or billions of years, it may drift inward or outward, subtly changing its galactic address. Our own sun may not be exactly where it was born. It likely formed in a cluster of stars within a giant molecular cloud and has since moved somewhat from that birthplace. Interstellar gas within the disk plays an essential role in sustaining rotation and renewal. Hydrogen gas extends far beyond the brightest stellar regions, forming a thin layer that can be detected through radio observations. In colder regions, hydrogen atoms pair into molecules, creating molecular hydrogen clouds that are the seeds of star formation. These clouds are not evenly distributed. They concentrate along spiral arms, where density waves compress the gas. When compression becomes sufficient, gravity takes over locally, and collapse begins. New stars ignite, injecting energy back into the surrounding medium. Massive stars emit strong ultraviolet radiation and stellar winds, carving cavities into the clouds. When they end their lives in supernova explosions, shock waves ripple outward, stirring the interstellar medium and sometimes triggering the next generation of collapse. This cycle of compression, ignition, expansion, and renewal continues as the disk turns. Over the span of one galactic year, entire generations of massive stars are born and die. Meanwhile, smaller stars like the Sun burn steadily for billions of years, quietly accompanying the disk in its orbit. The galaxy does not spin as a rigid object, but as a flowing system shaped by gravity, motion, and invisible mass. It is less like a wheel and more like a vast luminous current, each star tracing a path determined by the total gravitational field of everything else. As you rest and consider this, remember that even now, in this moment, you are traveling at 220 kilometers per second around the galactic center. The disk rotates, the gas drifts, the spiral arms glow softly with newborn stars, and the Milky Way continues its patient turning, an immense rotating ocean of light carrying us gently through the dark. Beyond the bright plane of the galactic disk, there is another structure that quietly shapes everything within it: the halo. While the thin and thick disks contain most of the visible stars arranged in orderly rotation, the halo is more diffuse, more ancient, and far less luminous. If you could step far outside the Milky Way and view it from a distance, you would see the glowing disk embedded inside a vast, roughly spherical envelope extending far beyond the visible edges. This halo stretches perhaps several 100,000 light-years outward, far past the spiral arms, and it contains some of the oldest known stars in the galaxy. Unlike the stars in the disk, which move in nearly circular orbits within a flattened plane, halo stars travel along elongated, tilted paths that take them high above and below the disk. Their motion is less orderly, more chaotic, reflecting a time when the Milky Way was still assembling from smaller protogalactic fragments. Many of these stars are extremely metal-poor, meaning they contain very small amounts of elements heavier than hydrogen and helium. In astronomy, metals include everything beyond helium, and their presence indicates previous generations of star formation. Halo stars formed early, before many supernovae had enriched the interstellar medium with heavier elements. In a sense, they are fossils of the early universe, preserving chemical signatures from billions of years ago. Scattered throughout the halo are globular clusters, dense spherical collections of hundreds of thousands, sometimes millions, of stars bound tightly by gravity. These clusters orbit the galactic center as coherent systems, passing above and below the disk in sweeping arcs. Some globular clusters are more than 12 billion years old, nearly as old as the universe itself. Their stars are tightly packed, far closer together than stars in our region of the disk. Yet the immense distances between individual stars still make direct collisions extremely rare. The halo also contains streams of stars, faint elongated trails that arc across the sky. These streams are remnants of smaller galaxies that were gravitationally captured and torn apart by the Milky Way. Over cosmic time, the Milky Way has grown not only by forming stars internally but also by merging with and absorbing dwarf galaxies. Each merger leaves behind subtle signatures, streams, ripples, and shifts in stellar motion that astronomers can map with precise measurements. One of the most important discoveries in modern galactic astronomy is that the halo is dominated not by visible stars, but by dark matter. While halo stars and globular clusters are observable, they account for only a small fraction of the halo's total mass. The majority exists as an invisible dark matter halo, extending far beyond the luminous galaxy. This dark matter halo provides the gravitational framework that holds the disk together and explains the flat rotation curve observed across large distances. Without it, the outer regions of the Milky Way would not remain gravitationally bound over billions of years. The dark matter halo does not emit light, absorb light, or interact electromagnetically in any detectable way. Its presence is inferred through gravitational effects. The speeds of stars, the motion of satellite galaxies, and the bending of light from distant objects. When astronomers calculate the total mass required to produce the observed motions, they consistently find far more mass than can be accounted for by visible matter alone. This unseen mass forms a vast gravitational reservoir in which the luminous galaxy is embedded. Within the halo orbit several small satellite galaxies, including dwarf spheroidal galaxies that are gravitationally bound to the Milky Way. These satellites move through the halo, occasionally interacting with the disk and contributing to its gradual growth. Over time, tidal forces stretch and disperse these smaller systems, adding their stars to the halo population. The Milky Way is not an isolated island. It exists within a dynamic environment where gravitational interactions shape its long-term evolution. When we step back and consider the disk, bulge, and halo together, we begin to see the Milky Way as a layered structure. The central bulge contains older stars densely packed around the core. The thin disk hosts spiral arms, gas clouds, and ongoing star formation. The thick disk preserves the memory of earlier dynamical heating and mergers. Surrounding all of this is the halo, a vast and ancient envelope of stars and dark matter that anchors the galaxy gravitationally. Even now, as the Sun continues its steady orbit within the Orion Arm, it moves not only through the disk but within this enormous halo of unseen mass. Every second, our solar system is influenced by the collective gravity of trillions of solar masses distributed across hundreds of thousands of light-years. And yet, from our perspective on Earth, the night sky appears calm and unchanging. The halo reminds us that what we see is only a fraction of what exists. The bright band of the Milky Way across the night sky is merely the inner luminous region of a far larger structure. Beyond that glow lies a dim sphere of ancient stars and an even more expansive ocean of dark matter, shaping the motion of everything within. In this way, the Milky Way is both visible and invisible, luminous and dark, structured and diffuse. Its disk rotates in quiet order, its halo drifts in ancient arcs, and together they form a gravitational system that has endured for billions of years and will continue turning long after our Sun completes many more galactic years. As we bring this journey through the Milky Way to a gentle close, it helps to gather everything into a single, quiet perspective. We began inside a rotating disk of stars, gas, and spiral arms, traveled outward into the ancient halo of globular clusters and dark matter, and traced the steady motion that carries our Sun around the galactic center once every 230 million years. Now, instead of focusing on one structure at a time, imagine the entire Milky Way at once. A luminous spiral galaxy about 100,000 light-years across, containing hundreds of billions of stars, embedded within a vast halo of unseen mass, and drifting through intergalactic space as part of a larger cosmic neighborhood. At its heart lies a compact and powerful object, the supermassive black hole known as Sagittarius A star. Though it contains about 4 million times the mass of the Sun, it is tiny compared to the total mass of the galaxy. It does not dominate the Milky Way in the way the Sun dominates the solar system. Instead, it sits at the dynamic center of the bulge, influencing stars that pass close by, while the overall structure of the galaxy is governed by the combined gravity of stars, gas, and dark matter spread across immense distances. Surrounding the bulge, the thin and thick disks rotate in differential motion, their stars tracing nearly circular paths shaped by the galaxy's gravitational field. Spiral arms form and reform as density waves move through the disk, compressing gas and igniting new generations of stars. Massive blue stars blaze briefly and explode, enriching the interstellar medium with heavier elements. Smaller stars like our Sun burn steadily for billions of years, orbiting quietly within the galactic plane. Above and below this bright disk stretches the halo, populated by ancient, metal-poor stars and globular clusters that preserve the memory of the early universe. Enveloping all of it is the dark matter halo, extending far beyond what we can see, providing the gravitational glue that holds the galaxy together. The Milky Way itself is not stationary. It belongs to a small collection of galaxies known as the Local Group, which includes the Great Spiral Andromeda Galaxy. Over billions of years, gravitational attraction is drawing the Milky Way and Andromeda toward one another. Their current separation of about 2.5 million light-years is slowly shrinking. In roughly 4 to 5 billion years, the two galaxies are expected to merge in a vast gravitational interaction, reshaping both systems into a new, larger galaxy. This future collision will unfold over hundreds of millions of years. Individual stars are so widely spaced that direct stellar collisions will be rare, but gravitational tides will distort the spiral structures, fling streams of stars outward, and eventually settle into a new equilibrium. Long before that distant event, however, the Sun will have completed many more galactic orbits. Each orbit carries the solar system through varying regions of the disk, sometimes passing near spiral arms, sometimes drifting between them. Over geological timescales, these passages may subtly influence the flux of nearby supernovae or interstellar clouds, but the galaxy's immense scale ensures that change is gradual. The Milky Way evolves, but it does so with cosmic patience. When we consider the galaxy as a whole, we see a balance between motion and stability. Stars orbit, gas cycles through phases of collapse and expansion. Dark matter exerts its silent pull, and the central black hole anchors the core. Yet the overall structure persists for billions of years. The spiral pattern may shift. Star formation rates may rise and fall. Satellite galaxies may be absorbed. Still, the Milky Way remains a coherent gravitational system, turning slowly in the dark. And within this turning system, on a small planet orbiting an ordinary star in a minor spiral arm, conscious beings have emerged who can measure the galaxy's rotation, map its structure, and infer the presence of invisible matter. We have learned that our Sun travels at about 220 kilometers per second around the galactic center, that the galaxy's mass is on the order of 1 trillion suns, and that most of that mass is unseen. We have traced the age of globular clusters back nearly to the beginning of cosmic history. We have imaged the shadow of the central black hole. All of this knowledge arises from observing faint light, subtle motions, and delicate gravitational effects across vast distances. And yet, despite the technical precision of astronomy, there remains something deeply humbling about the Milky Way. On clear nights, far from city lights, its pale band stretches across the sky as a soft river of stars. That faint glow is the inner disk viewed from within, the combined light of countless distant suns blending into a luminous haze. It is both ordinary and extraordinary. Ordinary because it is simply our home galaxy, extraordinary because of its immense scale and age. As this final reflection settles, remember that at this very moment you are moving with the Earth around the Sun at about 30 kilometers per second, with the Sun around the Milky Way at about 220 kilometers per second, and with the Milky Way itself through intergalactic space. Motion is constant, though we do not feel it. The galaxy turns, the halo drifts, the dark matter holds everything together, and time stretches across billions of years. In that quiet rotation, the Milky Way continues its patient journey, carrying us with it through the vast and silent cosmos. If we drift inward from the quiet spiral arms, past the Orion Spur where our sun circles at a comfortable distance of about 27,000 light-years from the core, the character of the Milky Way slowly changes. The stars grow denser, the light thickens, dust clouds gather in layered veils, and at the very center of this vast rotating system lies something both invisible and immense. Sagittarius, a star, the supermassive black hole anchoring our galaxy. Sagittarius A star contains a mass of roughly 4 million suns compressed into a region smaller than the orbit of Mercury. That number is almost too large to picture, so let us soften it into something more intuitive. Imagine the sun, whose mass defines the gravity of our solar system. Now imagine 4 million suns gathered together, not spread across space, but confined to a volume so compact that space and time themselves bend inward dramatically. That is the heart of the Milky Way. Black holes are defined by a boundary called the event horizon. This is not a physical surface but a limit in space-time. Cross it, and not even light traveling at 300,000 kilometers per second can return. The size of that boundary depends directly on mass. Physicists describe it using what is called the Schwarzschild radius. The idea is simple in principle. If you compress a given mass into a small enough sphere, there exists a radius at which the escape velocity equals the speed of light. Inside that radius, escape becomes impossible. For an object with 4 million solar masses like Sagittarius A star, that radius is about 12 million kilometers. That may sound enormous, but on galactic scales it is astonishingly small. 12 million kilometers is less than 1/10 of the distance between the Sun and Mercury. All the gravitational authority that guides the inner stars of our galaxy emerges from a region smaller than many stellar orbits. We cannot see Sagittarius A star directly because no light escapes from within its event horizon. But we see its presence through motion. Over decades, astronomers have tracked individual stars very close to the galactic center. These stars move at extraordinary speeds, tracing tight elliptical paths around something invisible. One such star completes an orbit in roughly 16 years. At its closest approach, it travels at several thousand kilometers per second, a few percent of the speed of light. These measurements are not abstract. They are precise. By mapping the orbit and applying Newton's law of gravity, refined by relativistic corrections, scientists calculate the mass required to hold that star in such a tight, rapid orbit. The answer consistently points to a compact object of about 4 million solar masses. There is no cluster of normal stars that could fit within that tiny volume without shining brilliantly. Only a black hole explains the data. Around Sagittarius A star lies a dense nuclear star cluster. Within just a few light years, millions of stars crowd together. Compare that to our neighborhood, where the nearest star lies more than 4 light years away. In the galactic center, the night sky from a nearby planet would blaze with starlight. The gravitational environment there is dynamic and intense. Stars interact, exchange energy, and occasionally are deflected into new trajectories. Gas clouds also drift inward. As they spiral closer to the black hole, tidal forces stretch and heat them. Friction within the gas raises temperatures to millions of degrees. In these moments, Sagittarius A star awakens briefly, emitting flares in X-rays and radio waves. Today it is relatively quiet, but evidence suggests that in the distant past it may have shone far more brightly, perhaps resembling a miniature quasar, pouring radiation into the inner galaxy. And yet, despite its power, Sagittarius A star does not dominate the Milky Way in the way one might imagine. The galaxy spans about 100,000 light-years. The black hole's direct gravitational influence extends strongly only across a few light-years. Beyond that, the combined gravity of billions of stars and vast halos of dark matter shapes the broader rotation. The black hole is the anchor of the center, but it is not the sole architect of the spiral. Still, its presence defines the geometry of the inner bulge. The Milky Way's central region is not spherical and smooth. It forms a bar-shaped structure, thick and elongated, rotating slowly. Over billions of years, gravitational interactions have sculpted this bar, redistributing angular momentum and guiding gas inward. The black hole sits at the intersection of these flows, a quiet focal point in a vast stellar current. Near the event horizon, gravity becomes extreme. If you could hover safely just outside, time itself would slow relative to distant observers. The deeper the gravitational well, the slower clocks tick. From afar, an object falling toward the event horizon appears to slow, fade, and freeze, its light stretched into longer wavelengths. From its own perspective, however, it crosses the boundary in finite time. This contrast is one of the most profound predictions of general relativity. Gravity shapes not only motion, but duration. Neutron stars, which pack about 1.5 solar masses into a sphere only about 20 kilometers wide, already demonstrate intense gravity. But Sagittarius A star exceeds even these extremes in total mass, though spread across a larger event horizon. It is a different category of object, not merely dense matter, but a region where space-time curves so sharply that all inward paths lead to a singular center. The galactic center, then, is not only a location in space. It is a demonstration of gravity in its most concentrated stable form. Stars orbit because space-time there is curved deeply. Gas flows inward because energy is redistributed through gravitational interactions. The structure of the bulge, the bar, and even the distribution of stellar populations all reflect billions of years of gravitational sculpting. And as we continue drifting inward in thought, we begin to see that this black hole is not an anomaly. Nearly every large galaxy we observe appears to host a supermassive black hole at its center. The Milky Way is not unique in this regard. The connection between galaxy growth and black hole growth hints at a deeper relationship. Gravity does not merely bind stars into spirals. It organizes structure across scales, from the smallest stable orbit to the architecture of entire galaxies. We will continue exploring how this central gravity shapes the wider Milky Way in the next segment of our journey. For now, imagine those inner stars moving in luminous loops around an invisible center, each orbit a quiet confirmation that something vast and unseen anchors our home galaxy. And if you are still traveling through the Milky Way with me, gently type 2 in the comments. As we remain near the galactic center, it helps to slow down and truly picture the environment within the innermost few light-years of the Milky Way. Out in the Orion Spur, where our sun moves at about 220 kilometers per second in a broad orbit lasting roughly 230 million years, gravity feels gentle and balanced. Stars are separated by vast distances. Encounters are rare, but near Sagittarius' star, the gravitational landscape becomes steeper, more dynamic, and more tightly wound. Within a sphere only a few light-years across, stellar densities rise to millions of times what we experience locally. Stars pass one another not at leisurely separations of trillions of kilometers, but sometimes within distances comparable to our outer solar system. Yet even here, the scale of space prevents constant collisions. What changes is not frequent impact, but gravitational interaction. Every orbit is subtly influenced by the collective pull of neighbors and, above all, by the dominant curvature created by the 4 million solar mass black hole at the center. The motion of these inner stars has been tracked for more than 2 decades using infrared telescopes capable of peering through intervening dust. One star in particular, often referred to as S2, follows an elongated elliptical orbit that brings it remarkably close to Sagittarius A star before swinging back outward. At its nearest approach, it travels at roughly 7,000 kilometers per second. That is more than 20 times faster than the Sun's motion around the galaxy. The period of its orbit, about 16 years, allows astronomers to observe an entire gravitational cycle within a human lifetime. From the size and timing of that orbit, the enclosed mass can be calculated. The result consistently converges on about 4 million times the mass of our Sun confined within a region smaller than our solar system. Moreover, precise measurements reveal small relativistic effects. As S2 swings through its closest point, its path shifts slightly from the perfect ellipse predicted by simple Newtonian gravity. This precession matches the corrections described by general relativity, confirming that spacetime curvature near Sagittarius A star is not merely theoretical but measurable. Even the light from the star is stretched to longer wavelengths as it climbs out of the deep gravitational well, a subtle gravitational redshift encoded in its spectrum. These observations transform the galactic center from a distant abstraction into a laboratory for extreme physics. Surrounding the black hole is a swirling environment of hot plasma, magnetic fields, and turbulent gas. Occasionally, clumps of material drift inward. As they spiral closer, friction and compression heat them to millions of degrees, causing brief flares visible in X-ray and radio wavelengths. Though Sagittarius A star is relatively quiet compared to the luminous quasars seen in distant galaxies, it is not entirely dormant. Evidence suggests that tens of thousands of years ago it may have experienced a more active phase, releasing jets or winds that inflated enormous structures above and below the galactic plane. Even today, faint gamma-ray lobes extend tens of thousands of light-years from the core, silent reminders that the central engine once burned brighter. Yet the black hole does not consume the galaxy. its gravitational dominance is profound only within a limited sphere. Beyond a few light-years, the mass of the surrounding bulge stars becomes comparable and then greater. On scales of thousands of light-years, it is the combined gravity of billions of stars and vast reservoirs of dark matter that governs rotation. The Milky Way's flat rotation curve, where stars far from the center orbit nearly as quickly as those closer in, cannot be explained by the black hole alone. Instead, an extended halo of unseen mass surrounds the entire galaxy, providing additional gravitational pull. In this way, Sagittarius A star is the anchor of the core, but not the architect of the outer spiral arms. Still, its presence influences long-term structure. The central bar of the Milky Way, an elongated concentration of stars stretching across the inner few thousand light-years, rotates slowly and channels gas inward along its length. Over cosmic time, this inflow feeds star formation in the inner regions and occasionally delivers matter toward the black hole itself. Gravity redistributes angular momentum, allowing some material to drift inward while other stars migrate outward. The result is a dynamic equilibrium, a constant reshaping guided by invisible curvature. In the deepest sense, the galactic center reveals how gravity sculpts structure without ever touching it directly. There are no ropes, no beams, no solid connections holding stars in orbit. There is only geometry. Mass bends space-time, and stars follow the straightest possible paths within that curvature. Near Sagittarius A star, those paths tighten dramatically. Farther out, they widen into graceful galactic arcs. From the tight 16-year loop of S2 to the 230 million-year galactic year of our Sun, every orbit is part of the same gravitational symphony, scaled across space and time. If we move even closer in imagination, approaching the boundary defined by the Schwarzschild radius of Sagittarius A star, we enter a conceptual region where intuition begins to fail and careful language becomes necessary. The Schwarzschild radius for a black hole of 4 million solar masses is about 12 million kilometers. That distance is calculated by taking twice the gravitational constant multiplied by the mass and dividing by the square of the speed of light. When expressed plainly, it means this: if all 4 million suns were compressed within a sphere about 24 million kilometers across, then the escape velocity at the surface would equal the speed of light. Nothing traveling slower than light could escape, and since nothing can travel faster than light, everything inside would remain inside. This radius does not represent a physical wall. There is no solid boundary, no surface you could stand on. Instead, it marks a point in space-time beyond which all future paths curve inward. Outside that radius, it is still possible, at least in theory, to fire a rocket outward and escape. Inside it, every possible direction leads deeper toward the center. The geometry itself tilts inward. For Sagittarius A star, this critical radius is tiny compared to the size of the galaxy, yet the curvature it represents is extreme. If our Sun were replaced by a black hole of equal mass, its Schwarzschild radius would be only about 3 kilometers. The Earth's orbit would remain essentially unchanged because the Sun's mass would be the same, only its size would differ. This comparison helps clarify something important. Black holes are not cosmic vacuum cleaners indiscriminately sucking in everything around them. Gravity depends on mass and distance. Sagittarius, a star, influences nearby stars dramatically because they venture very close. But if it were magically placed at the Sun's location with the same 4 million solar masses, the entire solar system would be violently disrupted, not because it is a black hole, but because 4 million suns of mass would now occupy the center. It is the mass that matters first. The event horizon defines how compact that mass has become. In the immediate surroundings of Sagittarius A star, stars experience strong tidal forces. Tidal force arises because gravity weakens with distance. The side of a star closer to the black hole feels a slightly stronger pull than the far side. If a star passes too near, this difference can stretch it, potentially pulling it apart in what astronomers call a tidal disruption event. The star would elongate, its gas stripped away and heated, producing a luminous flare before much of the material disappears beyond the event horizon. Such events are rare in the Milky Way today, but they are observed in other galaxies, offering glimpses of black holes actively feeding. The nuclear star cluster surrounding Sagittarius A star is itself a product of long-term gravitational evolution. Over billions of years, star clusters have migrated inward through a process known as dynamical friction. As a massive cluster moves through a sea of other stars, it gravitationally perturbs them, creating a wake of slightly enhanced density behind it. That wake exerts a drag, robbing the cluster of orbital energy and causing it to spiral inward. Gradually, these inward migrating systems contribute to the dense central population. In this way, gravity not only binds stars in orbit but slowly rearranges their distribution across cosmic timescales. The galactic center is also threaded with strong magnetic fields and permeated by high-energy particles. Supernova explosions in the crowded environment inject energy into the surrounding medium, stirring turbulence. Gas clouds collide, compress, and sometimes ignite new generations of stars, despite the intense gravitational background. It may seem paradoxical that star formation can occur so near a black hole, but gravity operates at many scales simultaneously. While the black hole dominates within a few light-years, smaller regions of gas can collapse under their own self-gravity if local conditions allow. Thus, even in the shadow of Sagittarius, a star, stellar birth and death continue. Observations made by radio interferometers have even resolved a bright ring-like structure around the black hole, produced by light bending around the event horizon before reaching us. This ring outlines the shadow of the black hole, slightly larger than the Schwarzschild radius due to gravitational lensing. Photons that skim near the event horizon can loop partially around it, tracing curved paths before escaping outward. What we see is not the black hole itself, but the imprint of its influence on light. The image confirms predictions made decades earlier. Space-time near a supermassive black hole behaves exactly as general relativity describes. And yet, beyond the drama of curved light and extreme speeds, there is a strange stillness. Sagittarius A star does not roar continuously. It sits at the center, quiet most of the time, a gravitational presence rather than a blazing beacon. Its power is expressed not in constant brightness, but in the steady orchestration of motion. The surrounding stars trace their paths year after year, decade after decade, century after century, responding to curvature that remains stable across human history. In this sense, the galactic center embodies both intensity and patience. Gravity there is overwhelming, yet its influence unfolds over immense spans of time. As we slowly widen our view from the immediate vicinity of Sagittarius A star, the deeper significance of the galactic center begins to emerge. A supermassive black hole of 4 million solar masses may dominate the innermost few light-years, but its true importance lies in how it participates in shaping structure across far larger scales. The Milky Way's central bulge, extending thousands of light-years outward, contains older stars packed into a thick, rounded distribution that transitions into a bar-shaped structure crossing the inner disk. This bar is not static. It rotates gradually, redistributing angular momentum among billions of stars. Over cosmic time, gravity within this rotating bar channels interstellar gas inward along elongated orbits. Some of that gas forms new stars in dense central regions. A small fraction drifts ever closer to Sagittarius A star, occasionally feeding it and triggering brief energetic episodes. In this way, the black hole and the galaxy are linked in a long gravitational conversation, each influencing the other across billions of years. The relationship between a galaxy and its central black hole appears to be more than coincidence. Observations of other galaxies show a striking pattern. The mass of the central supermassive black hole correlates with the velocity dispersion of stars in the galactic bulge. In simple terms, galaxies with more massive bulges tend to host more massive black holes. This suggests that as galaxies grow through mergers and accretion of gas, their central black holes grow alongside them. The growth may occur when gas funnels inward during galactic collisions, igniting luminous active phases. Although Sagittarius A star is currently quiet compared to the brilliant quasars seen in the distant universe, the Milky Way likely experienced more energetic chapters in its past. Subtle structures, such as large gamma-ray-emitting lobes extending above and below the galactic plane, hint that the center once released powerful outflows. Those outflows could have heated surrounding gas, regulating star formation in the inner regions. Gravity, therefore, does not merely confine matter. It can indirectly influence when and where stars are born by controlling how gas moves and accumulates. On even larger scales, the presence of a supermassive black hole reinforces the stability of the galactic core. As stars orbit within the bulge, close gravitational encounters gradually scatter some inward and some outward. The black hole acts as a deep central potential well, anchoring the distribution. While it does not dictate the motion of stars tens of thousands of light-years away, it defines the inner boundary conditions of the galaxy's gravitational field. Beyond the bulge, the disk spreads outward in spiral arms rich with gas, dust, and young stars. The rotation of this disk reveals another mystery. Stars far from the center move faster than expected if only visible matter were present. This discrepancy points to the existence of an extended halo of dark matter enveloping the galaxy. Thus, the Milky Way's structure is sculpted by multiple layers of gravity. The intense curvature near Sagittarius A star, the collective pull of billions of luminous stars, and the unseen mass of dark matter stretching far beyond the visible disk. Together they create the graceful, rotating spiral that defines our cosmic home. If we imagine hovering far above the Milky Way, watching it turn over hundreds of millions of years, the galactic center would appear as a bright, compact core around which the spiral arms unwind. The black hole itself would remain invisible, yet its presence would be encoded in the tight stellar orbits near the center and in the overall depth of the gravitational well. Every star in the galaxy, including our Sun, ultimately moves within a gravitational framework that traces back to that central mass concentration. Even though we are tens of thousands of light-years away, completing one orbit every 230 million years, our path is still part of the same vast structure anchored at the core. The story of Sagittarius A star is therefore not just about extreme physics in a distant region. It is about connection. The same gravitational law that governs the fall of an apple on Earth, that keeps the moon in orbit, that binds planets to the sun, also governs the motion of stars around a supermassive black hole. The scale changes dramatically, but the principle remains continuous. Mass curves space-time. Objects follow that curvature. From the 12 million kilometer Schwarzschild radius at the center to the 100,000 light-year span of the galactic disk, gravity shapes form without touch, guiding matter into patterns that persist across billions of years. As we conclude this passage through the heart of the Milky Way, imagine the dense cluster of stars near Sagittarius, a star tracing luminous ellipses in silent obedience to geometry. Imagine gas clouds spiraling inward, heating, glowing briefly, and fading. Imagine the bar rotating, the spiral arms sweeping outward, the dark matter halo extending unseen. All of it connected through gravity, all of it part of a structure vast beyond ordinary comprehension, yet governed by laws that are elegant and consistent. And if you are still traveling through the galaxy, still drifting in thought through its spiral arms and inward toward its hidden center, gently type 2 to show that you are still here, still moving through the Milky Way with us. Beyond the bright spiral disk of the Milky Way, beyond the glowing lanes of the Orion Spur and the sweeping arcs of the Sagittarius and Perseus arms, there is a quieter structure that most of us will never see directly. It does not blaze with newborn stars. It does not form bright blue clusters that light up the night sky. Instead, it surrounds everything like a vast, dim ocean. This is the galactic halo. The halo extends far beyond the visible disk, stretching well past 100,000 light-years from the galactic center. While the bright spiral may be about 100,000 light-years across, the halo reaches even farther, forming a nearly spherical envelope around the galaxy. If you could step far outside the Milky Way and look back, you would not see only a flat spiral. You would see a luminous whirlpool embedded inside a much larger, fainter sphere. Inside this halo drift some of the oldest stars in the galaxy. These stars move in long, tilted orbits, often plunging through the disk and rising high above it again. They do not follow the orderly rotation of the spiral arms. Some orbit in the opposite direction. Others trace elongated paths that carry them tens of thousands of light-years from the center before they fall back inward. Their motions are like memories, preserving the story of ancient mergers and long-forgotten collisions. Among the most striking inhabitants of the halo are globular clusters. The Milky Way contains more than 150 of these dense, spherical clusters. Each one is a tightly bound swarm of hundreds of thousands, sometimes millions, of stars packed into a region only a few dozen light-years across. Many of these clusters are more than 12 billion years old. They formed when the universe itself was young, not long after the first generations of stars began to shine. Globular clusters orbit the galactic center like distant lanterns circling a hidden fire. They are remarkably stable, their stars bound tightly by gravity. Their chemical composition reveals that they are metal-poor, meaning they formed before heavy elements were common. In their light, we glimpse a time before spiral arms fully formed, before the disk settled into its present shape. They are fossils of cosmic history, suspended in the halo's quiet expanse. But the visible stars and clusters are only part of the story. The true mass of the halo is dominated by something we cannot see. When astronomers measure how fast stars orbit the Milky Way at different distances from the center, they find something puzzling. According to simple gravitational expectations, stars farther out should move more slowly. If most of the galaxy's mass were concentrated in its bright central regions, then orbital speed should decrease with distance, much like planets in the solar system move more slowly the farther they are from the Sun. Yet that is not what we observe. Stars in the outer regions of the Milky Way orbit at roughly similar speeds to those much closer in. Instead of declining sharply, the rotation curve remains surprisingly flat. This means there must be far more mass spread throughout and beyond the visible disk than we can account for with stars, gas, and dust alone. This unseen mass is what we call dark matter. Dark matter does not emit light. It does not reflect or absorb it in ways we can easily detect. Yet its gravitational influence is undeniable. It forms a vast halo around the Milky Way, outweighing the visible matter by a significant margin. When we estimate the total mass of the Milky Way, including dark matter, we arrive at roughly 1 to 1.5 trillion times the mass of the Sun. Most of that mass is not in stars. It is in this invisible component. You can think of dark matter as the scaffolding of the galaxy. The luminous spiral arms are like glowing threads woven along an unseen framework. Without that hidden structure, the outer stars would not remain bound. They would drift away into intergalactic space. The halo's dark matter provides the gravitational glue that holds the galaxy together. This also explains why the halo extends so far beyond the bright disk. Dark matter is not concentrated only where stars shine. It forms a diffuse, enormous envelope that shapes the motion of everything inside it. The Milky Way's visible beauty is only a small fraction of its true size and mass. And so, when we look up at the faint band of the Milky Way on a moonless night, we are seeing only a thin slice of a much larger structure. Beyond the glow lies a vast, mostly invisible sphere, filled with ancient stars, globular clusters, stellar streams from shredded dwarf galaxies, and a deep reservoir of dark matter. Our galaxy is not just a spiral of light. It is a gravitational giant, extending far into the dark, shaped as much by what we cannot see as by what we can. In the next part, we will follow this dark matter-bound galaxy forward in time, toward an encounter already set in motion. A slow and inevitable approach with the Andromeda Galaxy, unfolding across billions of years. Far beyond the outermost stars of the Milky Way's disk, beyond even the furthest globular clusters drifting in their long elliptical paths, another galaxy is approaching. It is faint to the naked eye, a soft blur in the constellation of Andromeda, but it is vast, majestic, and bound to us by gravity. This is the Andromeda Galaxy, also known as M31, and it lies about 2.5 million light-years away. Though that distance sounds immense, on cosmic scales it is close enough that its motion toward us has already been carefully measured. Andromeda is not drifting randomly. It is moving toward the Milky Way at roughly 110 kilometers per second. That motion means that in about 4 to 5 billion years, the two great spiral galaxies will meet. This future collision is not a sudden crash but a slow gravitational dance unfolding across hundreds of millions of years. By the time it begins, our Sun will be about 9 billion years old, nearing the later stages of its roughly 10 billion year lifetime. The Sun formed about 4.6 billion years ago, and like most stars of its mass, it will spend about 10 billion years fusing hydrogen in its core before swelling into a red giant. So when Andromeda draws near, our solar system will still exist, but it will be approaching a profound transformation of its own. As the Milky Way and Andromeda approach, their dark matter halos will interact first. Long before their bright disks overlap, their extended halos, each stretching hundreds of thousands of light-years, will begin to feel each other's pull. Gravity will distort their shapes, drawing out long tidal tails of stars and gas. Yet, even during the closest passages, direct star-to-star collisions will be extraordinarily rare. The average distance between stars is so vast that even when galaxies merge, most stars simply pass by one another. Instead of individual crashes, the collision reshapes the large-scale structure. Orbits will be altered. Gas clouds will compress. New waves of star formation may ignite as interstellar material is stirred and squeezed. Over time, the two spirals will lose their distinct shapes and merge into a single, larger galaxy, likely an elliptical system sometimes nicknamed Milkomeda. This transformation will take billions of years. The first close approach may occur in roughly 4 billion years. Then the galaxies will swing past each other, pulled back by gravity, and eventually settle into one combined structure. The central black holes, each millions of times the mass of the Sun, will spiral toward one another and eventually merge, releasing enormous gravitational waves into space. Throughout this slow dance, the solar system's fate is uncertain in detail but not in broad outline. It is unlikely to be destroyed directly by stellar impact. More probable is that its orbit around the galactic center will change. The Sun could be flung into a more distant orbit, perhaps far from the dense central regions, or it might move closer inward. By that time, however, the Sun itself will be evolving. In roughly 5 billion years, it will exhaust the hydrogen in its core and begin to expand. As it becomes a red giant, it will swell outward, potentially engulfing Mercury and Venus, and dramatically altering Earth's environment. Long before any galactic merger fully settles, life on Earth as we know it will have ended due to the Sun's increasing luminosity. These overlapping timescales remind us that cosmic evolution unfolds on layers. The age of the universe is about 13.8 billion years. The Milky Way itself began forming over 13 billion years ago from smaller protogalactic fragments merging under gravity. Our Sun, by contrast, is middle-aged, less than half the age of the galaxy. A single galactic orbit for the Sun, about 225 to 250 million years, is called a galactic year. Since its birth, the Sun has completed only around 20 such orbits. In another 4 billion years, it will complete perhaps 15 to 20 more before the Andromeda encounter begins. These numbers stretch far beyond human history, beyond even the history of complex life. They remind us that galaxies evolve on timescales that dwarf civilizations. And yet, this evolution is not chaotic in a random sense. It follows gravity's patient logic. Dark matter halos merge. Gas clouds cool and collapse. Stars ignite, shine, and fade. The coming collision with Andromeda is not an anomaly but part of a larger pattern. The local group, the small collection of more than 50 galaxies to which the Milky Way belongs, is gravitationally bound. While the universe as a whole expands, driven by dark energy, our local region remains held together by mutual gravitational attraction. On very large scales, galaxies recede from one another as space itself expands. But within gravitationally bound systems like the local group, gravity overcomes that expansion. And so, even as distant galaxies drift away at increasing speeds, Andromeda approaches. The future of our galaxy is therefore shaped by two grand forces: the inward pull of gravity within bound systems, and the outward expansion of space on the largest scales. In the next part, we will look even further ahead, beyond the merger, beyond the Sun's lifetime, toward the long-term evolution of stars and the quiet future of a galaxy that is both ancient and still becoming something new. After the Milky Way and Andromeda complete their long gravitational dance, the result will not be a chaotic ruin but a new equilibrium. Over billions of years, the merged system will settle into a single, more massive galaxy, likely elliptical in shape, its once distinct spiral arms erased by repeated tidal distortions. The orderly disk that now defines our night sky will be gone, replaced by a smoother, more rounded distribution of stars orbiting in many directions. The dark matter halos that once surrounded two separate spirals will have blended into one, even larger halo, extending hundreds of thousands of light-years into space, continuing to dominate the total mass. Yet even this dramatic merger is only one chapter in a much longer story. Galaxies evolve not only through collisions but through the slow aging of their stars. Stars are not eternal. Their lifetimes depend mainly on their mass. Massive blue stars burn through their nuclear fuel quickly, living only a few million years before exploding as supernovae. Smaller stars, like red dwarfs, burn slowly and can shine for trillions of years. Our Sun, with a mass of 1 solar mass, sits between these extremes, destined for a main sequence lifetime of about 10 billion years. After it becomes a red giant and sheds its outer layers, it will leave behind a white dwarf, a dense remnant slowly cooling over immense spans of time. In the far future of the merged galaxy, star formation will gradually decline. Galaxies form new stars from cold gas clouds, but this supply is not endless. Each generation of stars locks up material in stellar remnants or expels it into space. During galactic mergers, bursts of star formation may briefly flare, triggered by compressed gas. But once the gas is heated or used up, the galaxy becomes quieter. Over tens of billions of years, the rate of new star birth will diminish. The brilliant blue stars that mark active star-forming regions will become rarer. The galaxy will redden as longer-lived, lower-mass stars dominate its light. Meanwhile, dark matter will continue to shape the structure invisibly. It does not burn or fade. It does not radiate away energy. Its influence persists as long as gravity governs motion. The merged galaxy's outer halo will remain a vast, diffuse envelope, holding ancient stars, stellar streams from earlier mergers, and countless dark matter particles moving silently through space. If we extend our thoughts even further, to times far beyond the current age of the universe, we enter an era sometimes called the Stelliferous Era's end. In roughly 100 billion years, most star formation in galaxies like ours will have effectively ceased. The universe will be populated mainly by dim red dwarfs, white dwarfs, neutron stars, and black holes. The brightest epochs of star birth will be long past. Yet, on those immense timescales, the red dwarfs will continue shining steadily, some for up to 1 trillion years. They will become the dominant sources of light in the cosmos. The night sky of any surviving planetary systems would look very different. Distant galaxies beyond the local group will have receded so far due to cosmic expansion that their light will no longer reach observers. The accelerating expansion of the universe, driven by dark energy, means that over time, more and more galaxies will slip beyond the observable horizon. Eventually, the merged Milky Way Andromeda galaxy and its nearby dwarf companions may be all that remains visible in the sky. Future astronomers, if any exist, might conclude that theirs is the only galaxy in existence, unaware of the vast cosmic web that once filled the observable universe. And yet, even in that deep future, gravity will still bind stars within their galaxy. Stellar remnants will orbit quietly. Occasional close encounters may eject stars into intergalactic space. Black holes at the center will continue to influence surrounding orbits. Over incomprehensible spans of time, gravitational interactions will gradually redistribute energy, slowly reshaping the internal structure. Nothing remains perfectly fixed. Evolution never truly stops. When we compare these cosmic timescales to human experience, the contrast is profound. Human history spans only a few thousand years. Civilization in its technological form only a few centuries. A single orbit of the Sun around the galactic center takes about 230 million years. The future merger with Andromeda unfolds across billions. The fading of star formation stretches tens of billions further. Yet all of it is part of one continuous process that began over 13 billion years ago when the first protogalaxies assembled under gravity's pull. The Milky Way is ancient, but it is not finished. It has already absorbed smaller galaxies, grown spiral arms, formed generations of stars, and built a dark matter halo that anchors it in space. It will merge again, reshape itself, dim, and persist in altered form. Change is not an interruption of its story. Change is the story. In the final reflection, we will return to the present moment, beneath our own quiet night sky, and consider what it means to belong to a galaxy that is both deeply old and still unfolding toward futures we can barely imagine. Now return to the present. Return to this moment, to the quiet rhythm of your breathing, to the soft awareness that above you, even if hidden by clouds or city lights, the Milky Way still stretches across the sky. It appears calm. It appears timeless. Yet everything we have explored reminds us that this galaxy is not frozen. It is ancient, yes, but it is also in motion, evolving slowly under the patient influence of gravity and time. The halo still surrounds us, extending far beyond what our eyes can see, reaching more than 100,000 light-years from the center and blending into an even larger dark matter envelope. Within it, globular clusters continue their long, looping orbits, each cluster a compact sphere of stars that formed more than 12 billion years ago. Some of those stars were already shining before the sun, before Earth, before the solar system even existed. They have completed countless circuits around the galactic core, moving silently through the halo while entire planetary systems formed and faded below them. The dark matter that dominates the galaxy's mass remains invisible but ever-present. It outweighs the visible stars and gas by several times, forming the gravitational foundation that holds everything together. Without it, the outer stars would drift away. With it, the Milky Way maintains its structure, its rotation, its coherence across immense distances. The spiral arms turn steadily. The sun continues its journey around the center, traveling at about 220 kilometers per second, completing one orbit roughly every 230 million years. Since its birth 4.6 billion years ago, the Sun has circled the galaxy only about 20 times. In cosmic terms, that is not many. Ahead lies the long approach of Andromeda, still millions of light-years away but already moving toward us. In about 4 to 5 billion years, the first close encounter will begin reshaping both galaxies. By then, the Sun will be nearing the end of its main sequence lifetime, approaching the final stages of its roughly 10 billion year span as a stable hydrogen-burning star. The timelines overlap in a quiet symmetry. As galaxies merge and transform, our own star will be transforming as well. Yet even that is not an ending in the grand sense. The merged galaxy will persist. Stellar remnants will glow faintly. Red dwarfs will shine for trillions of years. Gravity will continue weaving motion out of mass. When you look at the Milky Way in the night sky, you are seeing light from stars that may be hundreds or thousands of light-years away. That light began its journey long before many human events unfolded. And yet, on a larger scale, The entire visible band is only a thin slice of the galaxy's full extent. Beyond the glowing disk lies the halo. Beyond the halo lies intergalactic space. Beyond that, countless other galaxies, some already too distant for their future light ever to reach us because cosmic expansion carries them away. And still, here we are on a small planet orbiting an ordinary star in a spiral arm of a galaxy that is both massive and subtle. The Milky Way contains hundreds of billions of stars. It has grown through mergers, shaped by dark matter, stirred by gravity, illuminated by nuclear fusion. It has existed for over 13 billion years. Yet it is not complete. It is not static. It is a process unfolding across time. There is something quietly reassuring in that. The galaxy does not rush. It does not strain. It evolves through steady laws. Gravity drawing matter together, pressure balancing collapse, nuclear fusion converting hydrogen into helium, helium into heavier elements. Even the most dramatic events, supernovae and galactic collisions, unfold according to patterns written into the fabric of physics. Change happens, but it happens with structure. In the deep future, the night sky will look different. Spiral arms may be gone. The sun will have become a white dwarf. Distant galaxies will fade beyond the observable horizon. Yet the underlying truth remains. The Milky Way, in whatever form it takes, will continue its journey through time, shaped by forces that operate across billions of years. For now, though, we live in a rare and luminous era. Star formation is still active. The spiral arms are still defined. The halo still carries ancient clusters like quiet witnesses. We inhabit a galaxy that is mature but not old in the deepest cosmic sense. Dynamic yet stable enough for life to emerge and contemplate its surroundings. The Milky Way is both ancient and still evolving. It carries the memory of the early universe and the blueprint of its future within the same gravitational embrace. To belong to it is to belong to a story that began long before us and will continue long after, a story written not in words but in motion, mass, and time. If you have traveled through this entire quiet galactic journey tonight, from the bright disk to the dark halo and onward into the distant future, take a gentle breath and, before you rest, type 3 to mark the end of our voyage through the living cosmos.